Preparations and reactions of alkynes. Alkynes are organic compounds containing carbon-to-carbon triple bonds, one or more. Now, alkynes and alkenes behave very much alike in their chemistry, and I've recently posted on YouTube 3 videos on alkenes: preparations reactions, alkenes oxidation and reduction reactions, alkenes electrophilic addition reactions. And this video on alkynes will serve as a review of some of the reactions of alkenes, and at the same time these videos on alkenes will serve as a foundation for understanding the current video on alkynes. Alkenes and alkynes are quite similar in their physical and chemical properties. They're both hydrocarbons. They are both nucleophiles, electron donors. They're both nonpolar and insoluble in water, but soluble in nonpolar solvents. But there is one important difference we need to look at, and that's the acidity of terminal alkynes. Terminal alkynes are unusually acidic compared to other hydrocarbons. Here's a table comparing the acidity of various hydrocarbons. An alkane, a saturated hydrocarbon, has a pKa of about 55. That's about as non-acidic as you can possibly get. A terminal alkene, that is the hydrogens on a terminal alkene carbon, are still quite non-acidic, but a pKa of 44 is quite a bit more acidic. That's 10 to the 11 times more acidic than that of an alkane. And we get to a terminal alkyne, the hydrogen on a terminal alkyne carbon, still not particularly acidic, is surprisingly acidic, pKa 25. That's 10 to the 19 times more acidic than a terminal alkene, and 10 to the 30 times more acidic than that of an alkane. Now, just for comparison, here's water, which we consider to be neutral, pKa of about 16, and a strong acid like hydrogen chloride is -7. Now, I've drawn here the structures of the anions of an alkane, an alkene, and alkyne. As we've seen with many other acids, the key to understanding the acidity of an acid is really to look at the basicity of the conjugate bases of those acids. So I've listed here the pKb of the anion of an alkane, the anion of an alkene, and the anion of an alkyne. If we do the calculations, the pKb is 14 minus the pKa, so in the case of an anion of an alkane, we'll call it an alkane anion, pKb is -41. That's a very, very powerful base. The pKb of the alkene anion, -30, 14 minus 44. The pKb of a terminal alkyne anion, -11, which is still quite basic, but not nearly so basic as those above it. And of course, in the case of hydroxide, the pKb of the conjugate base of water would be -1.74, and the pKb of the conjugate base of hydrogen chloride, that being chloride, is +21, not basic at all. So as we look at these different structures, how do we reconcile these differences? Well, we could say that alkyl anions, like this methyl anion, this methide, is sp3 hybridized. That is, there are 4 electron clouds, and the pair of electrons is in one of those sp3 hybridized orbitals. In the case of the alkene anion, we can see that carbon is sp2 hybridized, and the non-bonded pair of electrons resides in one of those sp2 hybridized orbitals. In the case of an alkyne anion, this is sp hybridized. So we could say that the sp hybridized orbital in which the pair of electrons sits in an alkyne anion is 1/2 s character, that is made from one s and one p orbital. And that's more stable, less reactive, less basic than that of an alkenyl anion, which is in an sp2 hybridized orbital. That would be 1/3 S character, 2/3 P character. And that is indeed less basic, less reactive than an alkyl anion, in which its non-bonded pairs of electrons reside in an sp3 hybridized orbital, which is only 1/4 S character and 3/4 P character. The point here is that since S orbitals are lower in energy and nearer to the positively charged nucleus than are P orbitals, a negative charge, as we have in these anions, is stabilized to a greater extent in an orbital with a higher S character than in an orbital with a lower S character. And so alkynyl anions are therefore much more stable than alkenyl anions, which are in turn more stable than alkyl anions. So with an understanding of the acidity of terminal alkynes, we're ready to discuss the first of two preparations of alkynes. This is called the alkylation of an alkynide anion. And alkylation simply means adding an alkyl group to the anion of an alkyne, termed an alkynide. So we're starting here with terminal alkynes. Here's a generic terminal alkyne with one acidic hydrogen. And here's a specific example, a unique example, acetylene, which actually has two terminal alkyne hydrogens. We can deprotonate the terminal alkyne hydrogen with a very strong base such as sodium amide. Its pKb is -21, strong enough to react with these very weak acidic hydrogens. It's a typical acid-base reaction where the base donates a pair of electrons to form a covalent bond with the hydrogen. Hydrogen is monovalent. If it's going to bond with the nitrogen, it's got to break its bond with carbon, leaving the pair of electrons behind, forming the alkyne anion or alkynide. Similarly, with acetylene, it's no different. A second molecule of sodium amide would react in the same way. Now, I've only drawn one here for sake of space, so don't think that amide will react with two separate hydrogen ions. This would think of it as a separate sodium amide molecule reacting with the other alkyne hydrogen, forming again an alkynide anion. Now, alkynides are still quite basic. We can calculate that. The pKb of the conjugate base of an acid would be 14 minus the pKa. So 14 minus 25, in fact, alkynides have a pKb of -11. Strong base. Not as strong as amide, but still strong. Now, if you recall from the elimination reaction preparation of alkenes in the previous videos, strong bases are all good nucleophiles, and they undergo specific reactions with alkyl halides. In the case of a secondary or tertiary alkyl halide, elimination occurs, producing an alkene. But in the case of a methyl or primary alkyl halide, substitution occurs. And that's what we're going to carry out here. If we react our strong base alkynide anions with methyl or primary alkyl halides, we will get a substitution reaction in which the halogen is replaced by the alkynide, so we've added an alkyl group and made a longer alkyne. In the case of acetylene, it's still terminal because it has another terminal hydrogen on it. In the case of all other alkynides, same reaction occurs, a substitution reaction, the alkynide replaces the halogen, we'll wind up with a longer alkyne. In this case, it's internal. Well, let's get a little bit of practice with this. So write a reaction showing how the following transformation can be carried out by alkylation. So notice we have cyclopentyl ethyne as a starting material, and we're going to form 1-cyclopentyl 1-butyne as a product. Now, in order to do alkylation, we need a terminal alkyne. We can deprotonate that with sodium amide, forming the cyclopentyl ethynide anion. Strong base, good nucleophile. If we add a 2-carbon primary alkyl halide we can have a substitution reaction as we saw up here and add 2 more carbons, and that's done with ethyl bromide producing our longer alkyne product. Let's try one more, a little bit tougher. Write a reaction sequence showing how the following alkyne can be synthesized by alkylation. So the product has an alkyne, so that means that alkylation requires that either a carbon group was added on either side of the alkyne carbons. A carbon group is either added here or on the left here. Well, obviously the carbon group has not been added to the right, so the carbon group that was added to the alkyne must be this carbon group, this isobutyl group on the left, which means that our starting alkyne must have been ethyne or acetylene. We can deprotonate that with sodium amide, acid-base reaction, deprotonate the acidic hydrogen, either one makes no difference, forming the sodium acetylide anion. Strong base, good nucleophile, we need to add this isobutyl group as a halide, so we'd have isobutyl bromide or chloride, and it'll be a primary alkyl halide required to have a substitution SN2 reaction to produce our product 4-methyl-1-pentyne. Time for some practice. So the following reaction is incorrect. Explain why and show what product will form. So here I have sodium acetylide reacting with cyclopentyl chloride producing cyclopentyl ethyne. What's wrong with that? Well, in fact, it doesn't work. Why not? Well, the problem is that this alkyl halide is not methyl or primary. It's a secondary alkyl halide. And so the substitution reaction will fail. This carbanion cannot strike the backside of this alpha carbon because it's blocked. The alkyl groups are large and they block the backside of the carbon. So instead, this strong base will abstract a hydrogen ion, there it is, from the secondary alkyl halide. The pair of electrons falls back to form a pi bond as the leaving group leaves. Chloride is a fairly decent leaving group. So you get an elimination reaction rather than a substitution. In effect, you form these products. The alkynide is reprotonated back to acetylene. The alkyl chloride, instead of adding to the alkynide, is reduced to an alkene, a cyclopentene, and in effect the reaction has failed. So the moral is you must use a methyl or primary alkyl halide to carry out the alkylation reaction of an alkynide. So here's the second method of preparation of an alkyne. It's called double dehydrohalogenation. It means removing 2 hydrogen and halogen atoms. If we start with an alkene and halogenate it, we'll get a dihalide, then we carry out a double dehydrohalogenation of the dihalide. So here's an alkene. The addition of bromine or chlorine to the alkene has already been studied in the unit on alkene, so it won't be repeated here. It will give us a Vic dihalide. At this point, we can carry out the elimination reaction using KOH, a strong base, on a secondary or tertiary alkyl halide. This occurs essentially at room temperature. So with a secondary or tertiary alkyl halide, the alpha carbon is blocked. The hydroxide can't hit it by these bulky alkyl groups. And so instead, the hydroxide removes a hydrogen from a beta carbon, a carbon next to the alpha carbon. When the hydrogen ion is abstracted, the pair of electrons falls back and forms the pi bond in the alkene product. As long as there's a leaving group, bromide is a good leaving group. Then that gives us the alkene. But this alkene still has a hydrogen and halide on the alpha beta carbons. So a second elimination can take place using another equivalent of KOH, but notice the second elimination is much harder to do, requires a high temperature, 200 degrees C, to remove the second molecule of HBr, producing the alkyne. Recall that these reactions are concerted reactions, means that all three electron transfers in the elimination reaction occur simultaneously. If you used a stronger base than KOH, like sodium amide, the temperature can be reduced, but not a lot. It's still 150 degrees C for the second dehydrohalogenation. I want you to note that for this reaction to occur, a Vic dihalide is not the only possible starting material. You can also use a gem dihalide. So whereas a Vic dihalide means that the substituents are on adjacent carbons, a gem dihalide has the substituents on the same carbon. And the word gem derives from the Latin Gemini, and we have Gemini, which refers to twin stars, in fact. The process is the same. Our strong base, in this case I'll use sodium amide, can't strike the back of a secondary or tertiary alkyl halide here, and so it abstracts a hydrogen from the beta carbon. The pi bonds fall back, that is, the electrons fall back to form the pi bond. The leaving group leaves, giving us the alkene, on which we can carry out a second dehydrohalogenation using another equivalent of sodium amide at high temperature. The process is the same, giving us the alkyne. So let's get some practice with that. Can you write a reaction showing how styrene can be converted into a terminal alkyne and name the products? So here's styrene. We're not saying we're going to change the number of carbons. We're simply going to convert this alkene to an alkyne. Well, the process, as we saw above, is first to halogenate the alkene. We can either add bromine or chlorine. We'll form then 1,2-dibromoethyl benzene. Double dehydrohalogenation with two equivalents of KOH or sodium amide at a high temperature eliminates two molecules of HBr, giving us the terminal alkyne. Now, that's correct, but you should be asking yourself, wait a minute, how do we wind up with a terminal alkyne? How can the dehydrohalogenation occur on this primary carbon? We can see that the secondary carbon should undergo dehydrohalogenation here with these two hydrogen bromine atoms, but what about this primary? Didn't we say that goes by substitution? Well, at room temperature, the primary alkyl halide will only go by substitution. And the reason is, at substitution, at room temperature, the kinetic energy of the system is low. And the lowest energy path will be taken exclusively. The lowest energy path is substitution. It's only a 2-electron transfer. The elimination reaction requires a 3-electron transfer. It's a higher energy path, and so the substitution is preferred and pretty much exclusively at room temperature. Now, raise the temperature to 200 degrees C. All the molecules have enough energy to go by either path, substitution or elimination. Well, then you would ask, well, wouldn't we then get a mixture of both an alkyne and a substitution product? Well, you would if it were not for another factor. Let's consider the substitution reaction. If hydroxide strikes the backside of this primary carbon, and it can easily, it would displace bromide. Now, bromide, however, is not removed from solution. At high temperature, it has enough energy to collide back with the carbon and displace the hydroxide. That is normally a very difficult process to cause, but at high temperature, it can happen. The hydroxide has high energy at 200 degrees C, collides with the carbon and displaces the bromide. The bromide displaces the hydroxide. So this winds up being a reversible reaction in which bromide and hydroxide are continually replacing each other on the primary carbon. At the same time as that is going on, elimination will occur. That is, some hydroxide removes a hydrogen ion from a beta carbon, forming the alkene and displacing the bromide. Now that reaction is not reversible. As soon as that hydrogen ion is removed, it's neutralized by KOH, forming water. It goes well to completion. It's not reversible. So while the substitution reaction can't make up its mind where the product is, the elimination reaction step by step is removing all the HBr, and you wind up with complete elimination even on this primary alkyl halide owing to the high temperature. Okay, a little practice. Preparation of alkynes. Write a reaction sequence showing how the following transformation can be carried out. Name the products and intermediates. Here we're starting with propene. We want to go to 2-butyne. So we need to add one alkyl group. How do we add an alkyl group? Well, we add an alkyl group to an alkynide. So this has to be converted into an alkyne and then deprotonated to an alkynide. How are we going to convert this to an alkyne? Remember, the first step is halogenation. So either chlorine or bromine in dichloromethane will give us this intermediate 1,2-dibromopropane. Double dehydrohalogenation of this at high temperature, 2 KOH, 200 degrees C. Double dehydrohalogenation will give us propyne, 3-carbon alkyne, terminal alkyne. Let's remove the acidic hydrogen with sodium amide and form sodium propyneide, and then we can use this strong base, good nucleophile, to carry out the alkylation, the substitution reaction, with a 1-carbon halide, in this case methyl chloride would work, to give us 2-butyne. So let's look at some of the reactions of alkynes. We'll start with reduction reactions, namely hydrogenation. So the first kind is complete hydrogenation, that is saturation with hydrogen on a nickel, palladium, or platinum catalyst. So the alkyne has 2 pi bonds and requires 2 equivalents of hydrogen, but it's difficult to measure that out. It's just bubbled in as a gas, and so we just make sure we add excess hydrogen. And both pi bonds are saturated completely to the alkane. Now the mechanism of alkyne hydrogenation would be the same as the mechanism of alkene hydrogenation. So let's review that here. Using an alkene, a platinum catalyst, and hydrogen gas, the hydrogen gas adsorbs on the surface of the platinum and dissociates. And then the alkene pi bond open and the alkene adsorbs on the surface of the platinum. Then the hydrogen adds to the alkene. In place of the pi bond, it's a syn addition or same side addition. Now in the case of an alkyne, the syn addition of hydrogen occurs twice, producing a saturated alkane. A second type of hydrogenation of an alkyne is based on the fact that an alkyne is easier to reduce than an alkene. And so even in the presence of excess hydrogen, a deactivated palladium catalyst called Lindlar catalyst will stop the hydrogenation reaction at the alkene. And in fact, again, it's a syn addition, so potentially a cis alkene could be formed. So the mechanism of this hydrogenation is the same as that of complete hydrogenation, except that the alkyne reduction stops at the alkene. Only one of the 2 pi bonds are reduced. A third type of hydrogenation of alkynes is another partial hydrogenation, this time using sodium metal in liquid ammonia. Ammonia boils at -33 degrees C, so you can see liquid ammonia would be very cold. Leads to an anti-addition rather than a syn addition product. So an alkyne with sodium and liquid ammonia is a partial hydrogenation with an anti-addition product. I want to review the mechanism of hydrogenation with sodium and liquid ammonia. And this mechanism is not the subject of content for first year organic chemistry students. It would be an advanced level course, but I just present it here for interest. If you're not interested, skip ahead. If you are interested, just follow along. So indeed, sodium metal in liquid ammonia reduces alkynes to transalkenes, and I'll show you the mechanism for this. Now, sodium metal donates only one electron. It's in group 1a. It only has one valence electron. And so it's usually referred to as a reducing agent or a free radical rather than a Lewis base. Recall that Lewis bases are defined as electron pair donors. But I'm going to make the case that sodium is a strong base. I reckon its pKb is somewhere around -40, similar to an alkyl anion. And that single electron is donated to one of the alkyne carbons, and that's shown by a fish hook or a half arrowhead arrow. After that transfer, the pi bond breaks or cleaves homolytically, one electron in each direction. The pi electron that moved to the left side is a free radical, and the pi electron that moves to the right side joins with the other free radical to form an electron pair, a carbanion. This is a carbanion of an alkene. We saw before that that has a pKb of about -30, and that will react with ammonia, whose pKa is 35. Now, we recognize ammonia as a moderately strong base with a pKb of 4.8, but indeed it is a weak acid. Its hydrogens can be removed to produce sodium amide, and that would occur with a very strong base like an alkene anion. So let's look at the acid-base reaction. A pair of electrons from the base deprotonates the amine, leaving the pair of electrons behind to form sodium amide. And that removes or gets rid of our carbanion, but we still have a free radical on the other end. Now, a second atom of sodium donates another single electron, producing another carbanion, which is strongly basic, which reacts with a second molecule of ammonia, abstracting another proton and producing another molecule of sodium amide, and protonating our alkyne ultimately to a transalkene. Well, in this case it's trans, it's E2-butene, but in any case it would be an anti-addition product. Now, notice that in the very first step of the mechanism, the structure has already adopted a trans configuration. And you recall that for alkenes, a trans stereochemistry is more stable than a cis stereochemistry. And the reason for that is that these large alkyl groups are farther away from each other and less crowded. The term for that is steric hindrance. We say that this minimizes steric hindrance. And I would argue that the cold temperature favors the more stable alkene, transalkene structure and minimizes the steric hindrance or crowding. I think at higher temperatures you'd probably have a mixture of both cis and trans products formed. Well, hydrogenation mechanisms aside, let's get some practice predicting the products of reduction of an alkene and an alkyne in the same compound. This is both an alkene and an alkyne. Recall that in cyclic alkenes, the alkene carbons must be numbered 1 and 2. So here we have a methyl group on the third carbon, and on the first carbon we have a 1-propenyl group. Putting that all together, we have 3-methyl 1,1-propenyl cyclopentene. Let's look first at the case of excess hydrogenation with a standard catalyst that would saturate both the alkene and the alkyne pi bonds. Complete saturation would give us this product, which would be named 1-methyl 3-propyl cyclopentane. If instead we use hydrogen on Lindlar catalyst, recall that the alkyne stops reduction at the alkene, so the alkene is not reduced and only one of the pi bonds in the alkyne is reduced, giving us this product. Remember also that this is a same side addition leading to a cis alkene. This product would be called cis 3-methyl 1,1-propenyl cyclopentene. If instead of using Lindlar catalyst we use sodium and liquid ammonia, we'll get essentially the same product but with anti-addition. and this would be called trans 3-methyl-1,1-propenyl cyclopentene. Another reaction of alkynes is hydrohalogenation. So electrophiles, like the hydrogen halides, HCl, HBr, HI, will add to carbon-to-carbon pi bonds in alkynes, which are nucleophiles, electron donors, just as we saw as they were in alkenes. So let's go through the mechanism. Here's our electron donor, one of the pi bonds. On collision, donates a pair of electrons to the acidic hydrogen, electrophilic hydrogen. Hydrogen is monovalent, and so that reaction will go forward as long as bromine leaves. Bromine is a good leaving group, producing bromide. Now it turns out that the second atom in, the bromide, always winds up on the opposite side of the hydrogen that was added, which would imply that some kind of bridge formed. This is odd because the hydrogen that's added does not have any non-bonded electrons like we've seen in the past with bromine or chlorine or mercury, so it can't really form a bridge, but somehow it does, and it's believed to involve the other pi electron pair forming what's called then a pi complex, which forces an anti-addition product, like so. Now, the alkyne is more reactive than the alkene, as we saw with hydrogenation, and so if only one equivalent of hydrogen halide is added, the reaction stops at the vinyl halide, as we see here. We could then add a second mole of hydrogen halide to the vinyl halide, in which case we form a gem dihalide, as shown below. Here's our vinyl halide. Pi bond remains. It's nucleophilic. It donates a pair of electrons to the electrophilic hydrogen. Bromide is the leaving group. It's a good leaving group. Now the carbocation that forms does not form a pi complex, but it is stabilized by donation of a pair of electrons from bromine. Now in the past we've seen bromine donating electrons from an adjacent carbon to form a bridge. Now in this case the bromine is on the same carbon as the carbocation, and basically the same principle works. We would call this resonance. A pair of electrons can become a pi bond on the same atom. And this is more stable because every atom in this structure has a complete octet, as opposed to here where carbon has an incomplete valence shell. Next step is that bromide collides with our carbon that bears most of the positive charge in the intermediate, which was the carbocation, and that breaks the temporary pi bond, producing the gem dihalide. And of course the good thing about this as a student is that the formation of the bromonium ion intermediate prevents carbocation rearrangement, and the gem dihalide forms. Let's get some practice with hydrogenation of alkynes. So write the products of the following reactions and name the products. So here we have 3-methyl-1-butyne with one equivalent of HCl. Let's think through the mechanism. Hydrogen adds first to the less substituted carbon, Markovnikov's rule. Chloride adds second to the opposite side. We'll have an alkene. Will look like this. Now this will not be cis or trans because both substituents on this carbon are identical. Nevertheless, we can name this as 2-chloro-3-methyl-1-butene. Now if we added excess HCl instead of one equivalent, the reaction would not stop at the alkene. A second molecule of HCl would add. Hydrogen would add to the less substituted carbon and chloride to the more substituted carbon, giving us this product, which would be named 2,2-dichloro-3-methyl-butane. Write a reaction showing how the following transformation can be carried out and name the products. So here we have acetylene or ethine being converted to 2-bromopropene. Now notice that we've added one carbon, so that will involve an alkylation reaction of an alkyne ide. And The alkyne, recall, can be converted to an alkene halide if we add one equivalent of a hydrogen halide. So our process would look something like this. Let's go ahead and add sodium amide to deprotonate our terminal alkyne and make sodium acetylide or sodium ethynide. We need to add one more carbon to that. We can add methyl bromide or methyl chloride. There'll be a substitution reaction, SN2 reaction, replacing the bromide and adding the carbon. So there we get propyne. And to go from propyne to 2-bromopropene, we simply need to add one equivalent of HBr. Hydrogen will add to the less substituted carbon, bromine to the more substituted, giving us our finished product. Our next reaction of an alkyne is that of halogenation, specifically the addition of chlorine or bromine. Works pretty much the same way as we saw with alkenes. Carbon-to-carbon pi bonds are electron donors. They are nucleophiles. Now bromine and chlorine, they're not electrophilic. They are completely neutral and nonpolar, but they are polarizable. So in proximity to the electron donor, they do polarize. Electrons flee away from the bromine closest to the electron pair, producing dipoles, producing an electrophilic bromine. As the pi bond breaks and bonds to one bromine, the other bromine leaves as bromide, a good leaving group. Now, following Markovnikov's rule, the first atom in, the bromine adds to the less substituted carbon, producing the more stable, more substituted carbocation intermediate. As we've seen before, the bromine on the carbon adjacent to the carbocation can use one of its non-bond pairs of electrons to form a bridge and stabilize the intermediate from rearrangement. And that forces the bromide, the next atom in, to come in from the opposite side of the bridge, bonding to the carbon that was the carbocation and which bears most of the positive charge in the intermediate. The bridge will then break. It's temporary. The product at this point is a Vic dihalide, but it's a vinyl Vic dihalide. What happens with the second molecule of bromine? Well, the same process again. The pi bond, the alkene pi bond, will donate to the bromine. A bromine atom leaves as bromide. The bromine that adds to the less substituted carbon, producing the more stable carbocation. A adjacent carbon has a bromine which can stabilize the intermediate through the formation of a bromonium ion bridge. And finally, the second bromide added must come in from the opposite side of the bridge, breaking the temporary bridge and producing the tetrahaloalkane. So if you see a tetrahalo product, keep in mind that the way to produce that is by double halogenation of an alkyne. Now, unlike we saw with hydrogenation and hydrohalogenation, in the case of halogenation, it is not possible to stop the reaction at the dihalide. It keeps reacting. And so at least two equivalents of halogen are added to ensure complete conversion to the tetrahaloalkane. In other words, there's no way to stop this reaction at the vinylic Vic dihalide. It's time to get some practice with halogenation. So write a reaction sequence for the following transformation and name the products. So here we have cis 1,2-diphenylethene being transformed into 1,1,2,2-tetrachloro 1,2-diphenylethane. Quite a mouthful. Notice that the basic carbon structure is unchanged. In order to get the tetrahaloalkyl group, we'd have to halogenate an alkyne, which means that this has to be converted to an alkyne. How do you convert an alkene to an alkyne? Well, recall, first step is to halogenate either bromine or chlorine in dichloromethane will give us the Vic dihalide. This would be called 1,2-dibromo, 1,2-diphenylethane. We can then carry out a double dehydrohalogenation, 2 HBr molecules with 2 equivalents of KOH at 200 degrees C to give us the alkyne. This alkyne is diphenylethyne. To get to the tetrahalo product, we simply need to add 2 equivalents of chlorine, and we have it. Let's try the next one. Here, ethine is being converted to this tetrabromo substituted cyclopentane ring. So here's the parent compound, cyclopentane. Here is carbon 1, 2, and 3. So this is called 2,2,3,3 tetrabromopropyl cyclopentane. What a mouthful. Alright, notice there's quite a difference in the carbon structure. We've added this cyclopentyl methyl group to these 2 carbons. That would be done by an alkylation reaction, and then we have this tetrabromo group. That would be the bromination of the alkyne. So let's make the alkyne first, and we'll brominate it last. So how do we make the alkyne? We need to have an alkynide using sodium amide. We would deprotonate the terminal acidic hydrogen, producing sodium acetylide or sodium ethynide. Then we want to add our cyclopentyl methyl group to it. That would be a primary alkyl halide reacting with our strong base, good nucleophile, in a substitution reaction. This, by the way, is bromomethyl cyclopentane. Our product looks like this. So this would be carbon 1, 2, 3 cyclopentyl propyne. To get to our final product, simply a matter of adding 2 equivalents of bromine and dichloromethane, and we have our 2,2,3,3 tetrabromopropyl cyclopentane. Easier to do than it is to say. The next reaction of alkynes we want to study is Mercury-catalyzed hydration. And it's very much like the Oxymercuration-demercuration hydration mechanism of an alkene. And so we'll review that first before the alkyne. So recall we used mercury 2 acetate, and the alkene is the nucleophile. The pi bond breaks, bonding to mercury plus 2. Mercury 2 adds to the less substituted carbon, producing the more stable carbocation, Markovnikov's rule. Upon accepting that pair of electrons, mercury 2 is converted to mercury 1. Now mercury, like bromine and chlorine, has non-bonded pairs of electrons that it can donate to stabilize the carbocation intermediate and form a mercurium ion bridge that prevents carbocation rearrangement. Note that mercury has gone back to the plus 2 state after this. Now in this state, the carbon that bears most of the positive charge, when it collides with a water molecule, will break the mercurium ion bridge, which goes back to plus 1, and we have water added. That oxonium ion is deprotonated by another water molecule, producing the alcohol group. At this point, the reaction stops and waits for step 2, where we add sodium borohydride in basic solution. It releases hydride ion. The hydride ion displaces the mercury. The mercury plus 1 leaves with a pair of electrons and eliminates as mercury metal, elemental. So it's actually consumed in the reaction. We wind up with the neutral Markovnikov alcohol. Now the last step of this reaction I've shown as if it's a substitution, but in fact it's uncertain just how it works. It's thought perhaps to be a free radical mechanism, but I'm showing it for simplicity as a substitution reaction. Compare that with the Mercury-catalyzed hydration of an alkyne. This is done in a single step using mercury 2 sulfate, some sulfuric acid, and water altogether. Now in the case of mercury 2 acetate, it's unclear just how ionized mercury 2 acetate is. I've shown it as ionized for simplicity, but it probably is a combination of polar covalent and ionic bonds. In the case of mercury 2 sulfate, it's pretty much agreed that this is completely ionic, so I'm simply showing the mercury 2 salt ion. One of the pi bonds from the alkyne will break and form a bond with mercury 2. Mercury adds to the less substituted carbon, Markovnikov's rule, producing the more stable, more substituted cation intermediate. The mercury 1, since it has non-bonded pairs of electrons, will donate and form a mercurinium plus 2 bridge, which stabilizes the intermediate from rearrangement. Upon collision with a water molecule, the carbon that bears most of the positive charge in the bridge is bonded to, and the mercurinium bridge breaks, going back to mercury plus 1. Next step, just as we've seen above, is the oxonium ion is deprotonated by another water molecule, giving the neutral hydroxyl group, and we're left with mercury plus 1. Now, in the very same step, no separate reagents are added. Mercury leaves as mercury plus 2. So the pair of electrons from carbon to mercury are used to abstract a hydrogen ion from a hydronium ion, and mercury 1 leaves without its electrons as mercury plus 2. So the catalyst is regenerated. Mercury 2 is actually a catalyst. It's not consumed in the reaction the way it was in the Oxymercuration-demercuration reaction. At this point, we have a neutral alcohol that still has one pi bond in it. Since it's an alkene and an alcohol, it's named an enol. Now, this is the finished product, but an enol is more stable if it rearranges to a ketone, or at least a carbonyl form. And that's done like this. I'm simplifying a little bit, but the pi bond breaks to pick up the hydroxyl hydrogen, and the pair of electrons swings around to form the carbonyl, in this case, a ketone. Now, this is a reaction that first-year students aren't required to memorize or reproduce, but a general understanding of it would be worthwhile to help you predicting the products of hydration of alkenes as well as alkynes. So let's get some practice with the Mercury-catalyzed hydration reaction. So here we're starting with bromomethyl cyclopentane. We want to convert it to this ketone. Now, the very presence of a ketone should indicate that, should remind us that ketones are formed from hydration of an alkyne. Furthermore, there are 2 additional carbons in our product than there were in the original reagent, so that suggests we must have an alkylation step in here. So why not start with an alkyne? Ethyne would be 2 more carbons. We can carry that through deprotonation using a strong base, sodium amide. Either one of these hydrogens would be removed, producing sodium acetylide. We next need to add this bromomethyl cyclopentane group. Bromomethyl cyclopentane is a primary alkyl halide. SN2 reaction substitution would add it, giving us this 3-cyclopentyl propyne. To get from the alkyne to the ketone is simply a matter of the Mercury-catalyzed hydration reaction using mercury 2 sulfate, sulfuric acid, and water. Recall that the mercury 2 ion adds to the less substituted carbon, Markovnikov's rule, producing the more stable carbocation. Mercury forms a bridge, and water molecules add to what would have been the carbocation, breaking the bridge. The water is deprotonated, and eventually the hydroxyl group winds up here and mercury here. Eventually the mercury is replaced by a hydrogen, giving us this enol structure. Now, that is a neutral product, but it spontaneously rearranges to a more stable form. The pi bond picks up a hydrogen, which winds out here on the end, and the carbonyl group forms, and we get our final ketone product. This spontaneous rearrangement to another isomeric form is called tautomerization, a subject you'll deal with in a later course. The last type of reaction of alkynes we'll look at are a couple of different oxidations. And first of all, oxidation with cleavage. So alkynes, like alkenes, are cleaved by hot acidic or hot basic permanganate. An internal alkyne, like the one shown here, the carbons are bonded to only one other carbon. And just as with alkenes, these internal alkyne carbons are oxidized to carboxylic acids. So if this will cleave here, each alkyne carbon is bonded to one other carbon and therefore becomes a carboxylic acid. Since there are two of them, we get two equivalents of that as a product. This is an acidic solution. If it was done in basic solution, these carboxylic acids would be deprotonated to carboxylates. The other possible case is a terminal alkyne carbon with a hydrogen on it, and just as with alkenes, when the pi bonded carbon is bonded only to hydrogen, hot permanganate oxidizes it completely to carbon dioxide. The alkyne carbon on the left, which is bonded to only one carbon, is of course oxidized to a carboxylic acid, but since this is done in basic solution, the acid is deprotonated to the carboxylate. So, oxidation with cleavage practice. For the reaction sequence shown below, write the necessary reagents and conditions above the reaction arrows for each step of the reaction. We're starting out here with a secondary alcohol and going to styrene, an alkene. Now, that would be a dehydration reaction, which is carried out with sulfuric or phosphoric acid and heating, and that's dehydration, loss of water. In the next step, the alkene is converted to a Vic dihalide. That's done with the addition of, in this case, bromine and dichloromethane. From the Vic dihalide, we see that an alkyne is formed. To produce an alkyne, that would be a double dehydrohalogenation. That's done with two equivalents of KOH at 200 degrees C, the loss of 2 molecules of hydrogen bromide. Our next transformation takes our alkyne to a larger alkyne. We've added an alkyl group, one methyl group. This is clearly an alkylation reaction of an alkyne. The first step would be to deprotonate the terminal alkyne hydrogen with sodium amide and form an alkynide. The next step would be to add methyl chloride or methyl bromide such that a substitution reaction occurs to add the methyl group. And finally, you can see that our structure has been cleaved. We have a 2-carbon group on the right appearing as a carboxylic acid. Looks like hot acidic permanganate would cleave an internal alkyne into 2 carboxylic acids. The section on the left appears as benzoic acid, also a carboxylic acid. So hot acidic permanganate would do that last step for us. So the last reaction of alkynes that we're going to study is the oxidation without cleavage, sometimes called hydroxylation. Alkyne pi bonds, like those in alkenes, are oxidized to syn-diols by mild oxidation with permanganate, and that means in cold, that is not hot solution, but cool solution, room temperature, and neutral. So here is an alkyne, cold neutral permanganate. The intermediate that's formed, that can't be isolated, is a manganate ester, and there are 2 of these since we opened 2 pi bonds on the alkyne, giving a Vic tetraol. But this spontaneously loses water, 1 molecule of water for each pair of alcohol groups, giving this dicarbonyl compound. And since alkyl groups are on both sides, this is a diketone, a Vic diketone. So if in your studies you encounter a product that has adjacent carbonyls, think about the possibility that it may have been formed by a mild oxidation, hydroxylation of an alkyne. Let's get a little bit of practice here. This is an alkyne. It would be cyclohexylethine in cold neutral permanganate. Same as what we saw above. It's going to form the tetraol, a Vic tetraol, which loses 2 molecules of water and forms a dicarbonyl compound, in this case a ketone next to an aldehyde, since the terminal carbon on the right does not have an alkyl group attached. It comes out as an aldehyde. Last example here, I have a compound with an alkene and an alkyne together. So this is cyclobutene. It's got a 1-ethynyl group, so that would be 1-ethynyl cyclobutene. Let's consider hot, acidic permanganate solution. Recall that that will cleave sigma and pi bonds of alkenes as well as alkynes. Let's work from left to right. The alkene carbon on the left has only 1 alkyl group. It'll be oxidized to a carboxylic acid, as you see here. The alkene carbon on the right is attached to 2 alkyl groups, and so it'll be oxidized to a ketone, as we see here. Now the alkyne carbon on the left is bonded to 1 alkyl group, so it will be oxidized to a carboxylic acid, which we see here. And the alkyne carbon on the right, the terminal alkyne, is bonded only to a hydrogen, no alkyl groups, and so it will be completely oxidized to CO2 and water. And that concludes our study of alkyne preparations and reactions.